what I want to show you is maybe just a quick intro into simulating price data, because what's nice about simulations is that it gives you kind of a higher level understanding of what's actually happening in the price data, and then you can take this knowledge back and apply it to your prices. And one of the things that is really, really interesting is the sort of what you call a Brownian motion or a random walk, something like this. And it's effectively the idea that you got some person that is really drunk and just randomly walks through a park, and takes a step forward, a step left, and a step right, and so on. And so to model price series, one assumption is that we have a random walk, and the random walk basically has what we call, or the assumption is that we have normally distributed returns. Okay, so the first thing we need to do to maybe have a look at what normally distributed returns is to generate some of them. And NumPy again has pretty fantastic package. It's called random. So we can do np.random. And then what we can do is we go rand n, which is a normally distributed. And let's just say we get 1,000 values here. And we call this just R for return. I think that's a reasonable value. And so we can run this. And then what we can do is we can plot a histogram of this. And let's say we choose, say, 50 bins for our histogram. And so if you plot this, what you see is it looks a little bit, the Gaussian bell curve. So it looks a little bit like this, right? Gaussian, but not quite. But then, so I put a semicolon here so we don't plot the values. But then if I go from 1,000 values to say, let's see if we can run 1,000,000 and then run a histogram. I mean, this looks like almost like a perfect Gaussian bell curve, right? So the more samples you have, the more it approaches this, what we call the normal distribution or the Gaussian bell curve, right? And this is what you should do, because what you do is you draw random samples from a normal distribution and you make it. And so what we can do is we can now turn this into a price series, and we can basically generate something that actually looks like a real price. So let's go back, and instead of 1,000, 1,000,000, let's just generate 200 time steps. And so what we can do is now we can take the cumulative sum of this. And then what we can do is we can plot this. ELT.plot cumulative sum. All right. Well, this doesn't look too bad, right? It's quite believable that this could be a price. Okay. Now, one thing we could also do is, instead of, because right now it actually starts below 0. Okay. So don't like this very much. So what we could do is we can add 100. And so now here we've got time steps starting with 90 something and then just fluctuating. Okay. So we could do this again. And then again, just plot it. Boom, here we've got another one, and so on. Yeah. So these are all random series. One thing that's actually pretty cool is, let's just say we wrap this into a loop. Let's just say 100. And we run it. So hopefully, it's actually pretty fast. So what you see is really interesting here. We start at around 100, and then we see this interesting characteristic cone develop of all the different random price movements that could develop from here. Yeah. So if we maybe to 200, it's even more obvious. So we get basically a cross-section of all the possible paths up. No, this just started at 200, but we're still 100. So let's just go 200 here. And so this is often how we simulate. We basically say, well, given a certain random distribution of price returns, where could we potentially end up 200 time steps in the future? Mm-hmm. Okay, and this gives us this sort of distribution. Oh, okay, you know, obviously the most likely place we end up is here at 100, and then the others are less likely. Yeah, it's pretty cool, isn't it? Mm-hmm. We could also, for example, collect the final prices and put them into an array, and then look at the distribution of that. But if we only have 100, that will be a very rugged distribution.